When a molecule absorbs light, it becomes energetically excited. The excited molecule will move faster in some way, or if the light energy is high enough, absorption causes an electron to jump from a lower energy level to a higher energy level. When a molecule absorbs IR light, it becomes vibrationally excited. Let me explain. Molecules are in a continual state of motion, and there are three types of molecular motion. The first type is called translational motion. It occurs in gas and liquid states. For translational motion, a molecule travels in straight lines. That is, if a molecule travels from point A to point B, essentially in a straight line, we say it's undergoing translational motion. A second type of motion is rotational motion. If molecules are in a gas or liquid state, they will rotate about an axis. Basically, the molecule spins around and around like a top. The third type of molecular motion is called vibrational motion. The atoms and molecules oscillate back and forth about their bonds. That's called vibrational motion. Now, vibrational motion is, for all molecules, continual and incessant. It never stops, regardless of the temperature and the state of matter. Even at or approaching 0 degrees, or 0 Kelvin, I should say, even though all other molecular motion ceases, vibrational motion still persists. It never goes away. Now, also of importance, vibrational motions occur at specific characteristic frequencies. This depends on the bond type, whether the bond is single, double, or triple bond, and the nature of the atoms that are bonded. At ordinary temperatures, all vibrational frequencies in a molecule are at their lowest possible values, and these are called fundamental frequencies. Now, when an IR light beam passes through a sample of molecules, and the frequency of a given IR photon impinging on a vibrating bond matches the frequency of the vibrating bond, the photon is absorbed. The molecule, when it absorbs the photon, becomes vibrationally excited, and when it's vibrationally excited, the amplitude of the vibrational motion increases. Let's look at an example. Consider a molecule of carbon monoxide, shown here. It has just a single vibrational motion, where the CO bond lengthens and shortens over time. Now, the fundamental frequency for the carbon monoxide molecule is known. It's not important that you remember this, but it happens to be 6.5 times 10 to the 13 hertz. Hertz is a cycle per second. Now, if a photon comes along whose frequency is the same value, namely 6.5 times 10 to the 13 hertz, it impinges on the oscillating bond, and other conditions are met, that photon gets absorbed, the amplitude of the CO vibration will increase, and the CO molecule becomes vibrationally excited. Well, note that I said other conditions being met, so I need to elaborate. In order for an oscillating bond to absorb a light photon, there is an essential requirement. The vibrating molecule, as it turns out, must be an oscillating dipole. And by this I mean the molecule has to undergo a change in polarity during the course of the vibration, during one cycle of the vibration. Why is this so? Well, light is, at least in part, an oscillating electric field. If a molecule's oscillating bond is changing its polarity, it too will act as an oscillating electric field. When an oscillating electric field of a light photon meets an oscillating electric field of a molecule, the two fields can co-join, and the light photon can get absorbed. To explain this further, look again at the carbon monoxide molecule. Carbon monoxide, CO, is a polar molecule. The carbon bears a partial positive charge and the oxygen a partial negative. That's because the oxygen is more electronegative than carbon. Now, during a vibration cycle, as the CO bond lengthens and shortens, its dipole moment is going to increase and decrease. In other words, it's changing, and thus it becomes an oscillating electric field, and it can absorb a light photon. Now, let's contrast this with another molecule, a molecule of nitrogen, which is N2. Nitrogen molecule has two nitrogens that are triply bonded to each other. The molecule is a non-polar molecule. There's no positive, negative charges developed. And now during the course of its vibration, and its vibration also involves a lengthening, shortening, lengthening, shortening. During the course of vibration, it remains a non-polar molecule. There's no change in dipole moment during the vibration cycle of N2. Thus, it does not behave as an oscillating electric field, and it cannot absorb a light photon, even if the photon hitting it has the same frequency as the N2 vibration. And that's very important. Now, if a vibrating bond changes its polarity, it can absorb an IR photon. We say that that vibrating bond is IR active. If a given bond in a molecule, given its vibration, does not undergo a change in polarity, no change in dipole moment, we say that it is IR inactive. It can't absorb an IR photon. It cannot absorb an IR photon, even if there's a match in frequency between the photon and the vibrating bond. Now, one additional thing to point out. All forms of molecular energy, that's translational, rotational, vibrational energy, exist in discrete energy levels. Vibrational energy levels exist Vibrational energies exist in energy levels. The lowest vibrational energy level corresponds to the fundamental vibrational frequency that we mentioned before. When a light photon is absorbed by a vibrating bond, the vibrating molecule moves from the fundamental level to the next higher vibrational level. Now, before we examine the details of IR light absorption, I need to explain one more facet. Vibrational motions in molecules fall into two categories: stretching motion and bending motion. In stretching motion, a bond or set of bonds lengthen and shorten with time. This is what we saw with the carbon monoxide vibration, the CO vibration. So the continual lengthening, shortening of a bond or set of bonds is called stretching motion. The second kind of vibrational motion is bending motion, and this occurs with a set of three or more atoms. When you have, let's say, three atoms, there is a bond angle. In the bending motion, the bond angle increases and decreases, decreases with time. It's like a pair of scissors opening and closing over time. That kind of motion is important in molecules, and we call it a bending motion.